So what I'll try to do is go into a little bit more detail on diffuse optical spectroscopy and how we use spectroscopic techniques in diffuse optics to also do imaging. And just some disclosures. I think probably a lot of you know by now that we work with different companies and have started different companies, so I'm affiliated with these companies. Medical imaging. So probably a topic that you haven't really talked about, the sort of the larger context of diffuse optics or optics in general in medicine. And what kind of when you stand outside the field, you see that we really are kind of like a parenthetical statement in medical imaging. MR, X-ray, nuclear, ultrasound, those are the mainstream radiologic modalities. And optical imaging, if you go to a radiology department and you say, I work in medical optical imaging, they will be puzzled. Maybe people will eventually arrive at endoscopy as an example of medical optical imaging. But most people in mainstream medical imaging are not really thinking of optics as a modality. It's kind of in biomedical engineering labs, it's in chemistry departments, physics departments, but it hasn't really permeated the medical community except for one thing. In some ways, it's actually everywhere. So when I first started working in the field, there was very little market for medical optical devices. This was in the early 80s. There were lasers that could cut tissues, like CO2 lasers, YAG lasers. There were certainly argon ion lasers. All of these were really big, high-powered lasers. They required water circulation for the most part to keep them cool, consuming lots of power. But with advances in that technology and, of course, integrated circuits and miniaturization of processors, things have really, really changed. So now we have over a $60 billion per year market in medical optics. That number, it's really difficult to sort of get an exact estimate of that number, but I think that's a pretty conservative estimate based on looking at two sort of broad areas, diagnostics and therapeutics. In diagnostics, devices are in both imaging and spectroscopy. There's really very little that does spectroscopic imaging, all of the contrast elements that are available from spectroscopy. And broadly speaking, they're kind of separated into a few categories. One is tissue oximetry, primarily using near-infrared technologies. So these devices, Vioptics, Massimo, Medtronic, Covidien, these are all tissue oximeters. And primarily they're contact-based, well, these are all contact-based probes, and they work in the near-infrared, and they measure oxy and deoxyhemoglobin. But the output is a clinical endpoint called tissue oxygenation, which is a relative measure of oxyhemoglobin divided by total. You can measure that in tissue, or you can measure that just on the arterial side, and if you do that, then it's called a pulse oximeter. OCT is alone about $1 billion a year market. By the way, the near-infrared oximeters are about $1 billion a year market. OCT, both in the eye, it's really revolutionized ophthalmic imaging. Now you can image all the way from the anterior segment to the posterior and do that at very high resolution, get beautiful cross-sectional views in fractions of a second. You can even use it to guide surgery. You can do angiography with OCT and look at vascular structure and flow. So this is really transformational. The next big target area is intravascular OCT. So many of you may be familiar with that. The use of OCT probes to go inside of blood vessels and form a 3D view of the lumen of a coronary artery or, let's say, a blood vessel in the brain. Anywhere where you have a blood vessel, then you can look at the inner wall. And the combination of OCT with intravascular ultrasound appears to be a very powerful approach, growing rapidly. Then there are endoscopic approaches. So Novadaq is a publicly traded company, and they make devices that are primarily based on fluorescence. So looking at an exogenous fluorescence contrast agent, indocyanine green, That's a very good way to image perfusion. It's a pretty standard technology, so it's not, none of these technologies are super sophisticated or state-of-the-art, but they're used every day in patient studies, and they really make a difference in outcome in a variety of settings. And I think, of course, many of you know that this technology from Novadaq has been licensed to Intuitive Surgical. So Intuitive Surgical uses this in the Da Vinci robot to help guide surgery, identify perfusion, look at reanastomosis of tissues as you reconnect one tissue to another. So it's a really important technology for that. That can also be done using intrinsic signals. And Perimed, have any of you heard of the company Perimed? Just Chris. So this is a really interesting company. They're number one. They've been kind of the key developer of laser Doppler techniques. And laser Doppler technologies have increasingly become more and more quantitative and model-based in the research lab. But out there in the commercial marketplace, there's still relative measurements of flow. They've also extended this to wide field imaging. So they have wide field laser Doppler imagers. And now they're kind of getting rid of the wide field laser Doppler imagers. And they're moving towards, what would you guys do if you wanted to get rid of laser Doppler now that you've had a week of the class? But you want to measure flow. This is your test question to see if you've been paying attention all week. What signal would be good for flow measurement? Okay, I'll have to help. Speckle. So they're making very nice, stable, very high signal to noise laser speckle imagers. So the Periscan and a whole series of devices are coming out that they're manufacturing. And I had a chance to visit them in Sweden. They're in Stockholm. I was there in June. So really, really interesting company. And they've been in business making and selling laser Doppler and laser speckle imaging devices, you'd be surprised, since the early 80s. So they have a company of about 70 or 80 people, and they've been selling devices all around the world. Of course, endoscopy. That's an important optical imaging approach, and increasingly people are trying to introduce new contrast elements in endoscopy. Obvious ones are looking at spectral control, but also looking at exogenous contrast agents with endoscopes. And so this is kind of where things fuse together with the Novadaq device. So these are all the broad classes of imaging and spectroscopy technologies that are used in diagnostics, that are optically based, that are used every day. And for me, this is always remarkable because when I started working in this area, there may have been a market of, I don't know, 100 million, a few $100 million per year selling primarily surgical lasers. And now all of these technologies are widely used and they're growing. So all these markets are predicted to grow. And the growth will be driven in part by new things, the kinds of stuff that are being discussed in the course, new needs, better understanding of how these things work. And I don't want to skip the therapeutic side. We're not really discussing much of that in this course, but just to remind you that therapeutic medical lasers are on their own about $1 billion a year market. And they're predicted to grow. Well, they're growing, not just predicted to grow, in a variety of different ways. The lasers are becoming more compact and more powerful and more versatile. They're being combined with imaging approaches to give better feedback and control so that everybody can do laser surgery as well as the expert at the Beckman Laser Institute. Stuart Nelson is one of the I usually hold him up as the expert. He's been doing laser medical surgery procedures for like 25 years. And how he gets a great outcome for a patient is not necessarily well understood, but we've been imaging what goes on when he treats patients and using those images as an endpoint to then predict outcome is a really new frontier. And it doesn't sound all that revolutionary when you think about it, but virtually little or no imaging has been done and spectroscopy has been done as a guide for therapeutic procedures. So those are opportunities for all of you. The most common outpatient surgery done in the US is ophthalmic surgery. And if you think of the sophistication in all laser LASIK. How many of you are familiar with all laser LASIK? So why is all laser LASIK insanely sophisticated? You just heard of it? So Vasan, help us out.
Well, you have a laser device to basically make a thin cut on the top of the cornea to expose the corneal stroma, and then there's a different laser that's used to actually ablate the cornea to do vision.
And that first laser, what kind of a laser is that? That's a femtosecond laser. So how many of you are familiar or ever thought that femtosecond lasers were used in the most common surgical procedure that were done in the United States? It's kind of mind-blowing, because for sure, when I started working in this field, not only were there no femtosecond lasers, actually no one really thought that there would be femtosecond. I'm sure some people thought that we could develop femtosecond lasers for telecommunications at some point in the future, because the shorter the pulse, the more information that you can pack, and and so that's one of the driving forces. But now one of the big drivers for femtosecond technologies are medical applications. Yes?
I just might add that the technology of femtosecond lasers have become so sophisticated and so routine in some way that the optics that go into coupling the light in the eye is actually more expensive
Yes.
than the laser source itself.
Yes. You can make those lasers now out of strands of glass. Of course, those lasers are not the ones that are used to do the cut. They don't generate enough power. But certainly all fiber femtosecond lasers, it's pretty remarkable to see the growth in that. So I think this is your particular good news. This is your good news slide for all of you who are young and starting your careers. I think there's a horizon out there, and part of the horizon is you may not work in the commercial sector, although some of you do, of course, but to have a robust, a healthy commercial sector is extremely important for the academic side, because if we don't have places where graduates can go and get jobs and create a growth in the economy, then we're all in trouble. So this is really, really important. And although I won't get into it in this lecture, and we can talk about it over In-N-Out Burger, perhaps, at noon. But these technologies are very, very well suited. They're coming along and advancing at a time when there's a big transformation in healthcare in the United States, which is really pushing to develop solutions that are much more cost-effective and even preventative to keep people out of hospitals. So optics is very, very conducive to that. I'm just going to talk today about this class of diagnostic technologies, oximetry, but I'll take it a little further and talk about not just oximetry, but what's next beyond oximetry and how to be very quantitative. And that's the area of diffuse optics, which of course you've been modeling and working on all week, light propagation in biological tissues. This is an illustration of diffuse optics. It's actually a real measurement. So this is a picture of me with a couple of 850 nanometer near-infrared LEDs in my mouth. And I've been taking this same picture of me for almost 25 years. When I first bought a $40,000 thermoelectrically cooled zero-defect CCD camera in about 1991, one of the first things that we did was stick a flashlight in my mouth and take a picture. And I looked the same from the inside over 20 years. Things just changed on the outside. So this is a picture where essentially the camera, that was a $40,000 camera, and I should have put that picture up, but I do have it. The camera at the time, super expensive, cooled, slow scan CCD. The camera that we used for this picture, anybody want to take a guess how much that cost? Exactly, $200. It was a Canon Rebel with the IR blocking filter removed so that you could see the 850. So there's no external illumination. All the light is coming from the inside. And you can see some interesting things. This is always spooky to see the pupils, the light coming out from there. This little shadow over here is a nevus. That was there 25 years ago. I think it's a nevus on my retina. I had our retinal specialist confirm that I do have one, and it's possible that it is that shadow. So it's not absolute confirmation, but it's quite possible. So you can see there's a lot of light propagating over several centimeters, going through soft tissue, hard tissue. This gives you an appreciation that there's a lot of light that's available for detection. It also gives you a really strong understanding that it's very difficult to be quantitative about this unless we can look at the history of the photons, or we could control the path length. We could figure out where the light has been. So lots of light, that's a good thing. Have no idea where it came from, that's a bad thing. I told you that the light source was in my mouth, but if I didn't tell you that, just from this picture, could you predict it? No, there's no way really of knowing. It's completely randomized. All the optical phase relationships are totally random with respect to one another. This is another example of diffuse optics where we use structured light. And the key with all of these methods is we want to use as many wavelengths as possible to get contrast from endogenous components. We want to structure the light in space and time. So that means we'll introduce in this technique, spatial frequency domain, which you've already heard about, structuring of light in space. In this technique, we'll introduce structuring of light in time. So the key with all of these is really we want to measure optical path length. And this is sort of the canonical example I think most of you are familiar with, so I won't spend a lot of time on it. But if we have a cuvette and we put it in a spectrophotometer and we measure the attenuation of the light on the other side, we can calculate the concentration of what's in the cuvette just by measuring the absorption coefficient or looking at the transmission loss. And the thing is here, we're assuming that the path length is fixed. The cuvette defines the path length. We're assuming we know the molar extinction coefficient. And we're assuming that there is no scattering in this material because scattering will mess everything up. So here's a picture of scattering. Light comes in, it bounces around multiply. We have our detector on the other side. The scattering increases the path length of the photons. They travel further. Therefore, they are attenuating some of this signal. And the absorption is attenuating some of the signal. So our key challenge, and something I've been obsessed with for about 25 years, is to separate light absorption from light scattering. If you can do that, if you can do scatter-corrected spectroscopy, then you can look inside the body and treat the body as if it were a cuvette. So from a physics point of view, that's our goal, separate absorption from scattering. And ideally, if we measure path length, we might be able to localize information in 3D and do tomography. From a physiology point of view, that means that we could use those wavelengths to determine perfusion and metabolism at depth. So perfusion and metabolism are encoded or revealed in the oxy and deoxyhemoglobin signals. We can also determine the concentration of any other near-infrared absorbers or fluorophores. So indocyanine green, that's also a near-infrared absorber and a fluorophore. We can look at lipids and water since they have very nice signatures in the near-infrared. And water, lipid, oxy, and deoxyhemoglobin account for a little more than 80% of tissue composition anyway. So that really does a great job of characterizing biochemical constituents. And any other exogenous dyes or particles, and as some of you know, are any of you working on exogenous contrast agents? Well, you're kind of in the minority, but I guess it's not surprising considering you came to a class, a workshop on light propagation in biological tissues, but there's so many people in our field in biophotonics that are working on exogenous agents, from nanoparticles to organic dyes, encapsulated agents, gold nanoparticles. You know, it's just, there's a huge amount of work going on. And then there are already some grandfathered in agents that are used, like indocyanine green, methylene blue. Has anyone heard of Lymph Assurance? Lymph Assurance. So that's a blue dye that surgeons use, breast surgeons, actually many surgeons use every day to visualize lymph nodes. They just inject it just right into the skin and it drains into the sentinel lymph node and then they can see it with their eyes. So it's typically not used to find lymph nodes that are buried like 3 centimeters beneath the tissue, but when they're doing surgery, after they've more or less localized the lymph node with radioisotope, then it helps them track the flow of lymph and then localize the lymph node just by seeing the blue dye. So there's already a lot of stuff that's being used. There are already a lot of natural products that do have optical contrast. And so those can be integrated into and with these technologies. Also, fluorescence, if you're doing deep tissue fluorescence and you want to quantify the fluorescence, fluorescence is, one of the nice things about it is that people use it, they just grab the signal as fast as they can, and they don't worry about being quantitative. So if something lights up, then probably, and it's inside the blood vessels, then there's blood flowing. But you can go one step further, and you can be quantitative about fluorescence. The fluorescence may extravasate from the blood vessels and then get taken up or get localized into a tumor. And maybe you want to quantitatively compare the contrast between that tumor and the surrounding tissue. So to be quantitative, the optical properties of the tissue distort the fluorescence. They distort the excitation light going in, so they changes the intensity of the excitation going into the tissue, and then the optical properties of the tissue will distort the fluorescence coming out. So if you know both the optical properties at the excitation and the emission side, you can correct for those distortions and then be quantitative about the fluorescence inside the tissue. So these are all good reasons to know tissue optics and optical properties and characterize them. So from an academic point of view, there are basically, we've sort of categorized optical path length technologies into sort of three major approaches. There are three ways to control optical path length. The first is to control the wavelength. So I think everybody intuitively knows that visible light doesn't go as deep into tissue as near-infrared light. And we kind of showed an example of that with the 850 nanometer LEDs bouncing around. The light is coming out of my face, going several centimeters. If that were blue light or green light, would you see anything? Nothing. It wouldn't go very far. So the penetration depth, the 1/E penetration depth of light in the blue and the green is on the order of a few millimeters, a millimeter, fraction of a millimeter. It depends on the actual wavelength. But if we talk about it in terms of path length, the absorption length, that's the average distance between absorption events, and the scattering length, the average distance between scattering events, they're comparable. So we have a mean path length that may only be a few millimeters. And then as you go from the visible into the near-infrared, from 570 or so to a little over 650, you get this dramatic 15, 20-fold change in optical path length. So that wavelength-dependent path length is a way of controlling path length if you're trying to do an experiment. In other words, if I'm scanning my optical wavelengths across the visible into the near-infrared, and I look at the wavelength-dependent signal, I'm actually interrogating at different depths in the tissue. And even if I change the tissue oxygenation state, so if I go from 100% saturation down to 50% back and forth, so that's dynamic physiology. The path length will change by another factor of 2. So we can use spectroscopy to control the path length and also interpret and gain information from where the signals are in tissue. And this is a very dramatic illustration, I think, of that concept. So bring us back to the real world. This is just a picture of me illuminated with 400 nanometer light, where absorption and scattering are roughly, the absorption and scattering lengths are approximately equal. And you see a lot of contrast here. And here is, again, external illumination, 850 nanometer light. The absorption lengths are much, much greater than the scattering lengths. They're actually in the near-infrared, an absorption length, which is the average distance between absorption events. It's not the average distance between molecules, per se. It's the average distance between events. So in the near-infrared, those absorption lengths may be about 10 centimeters. They're very far apart. Whereas scattering lengths in the near-infrared are 20 to 40 microns. So huge difference. Obviously, I look better in the near-infrared. So what is all this contrast, and where is it coming from? Melanin. It's coming from melanin. and other sort of cutaneous epidermal distortions that have occurred as a consequence primarily of solar irradiation. In other words, skin damage. So this is all coming from very superficial structures. Where is the melanin located? Did you say dermis?
Epidermis.
Epidermis. All right, epidermis. So how deep is the melanin?
It goes down to 200 microns.
200 is already getting way too deep. I mean, of course, there actually is a little bit of dermal melanin, but the primary contributor to all of this stuff is epidermal melanin. So any guesses on how deep that is? I know exactly how deep that is in my skin because we measure it with multiphoton microscopy. Just to blurt out a number.
50 microns.
50 microns, perfect. I knew somebody knew. So that's insane. So all the contrast in this image is coming predominantly from absorbers that are attenuating the light 50 microns deep in the tissue. And where's the contrast coming from here? First of all, there's not that much contrast. So that's a good thing. I do look better. And cosmetic companies are trying to, they try to figure out how to put stuff on your face so that there is multiple light scattering, and it gets rid of all this contrast, and it makes you look a little bit more like this. So that's exactly what they do. All of this contrast comes from diffuse light. So light propagating deep into the tissue, it bypasses the melanin, so we don't see all that melanin contrast. It scatters multiply, comes back out, and it carries information content on what principal chromophores. That's a super rhetorical question. Exactly, the hemoglobin, the oxy and deoxy. Well, this is 850, so it's primarily going to be oxyhemoglobin. So that's a really, I think, a very dramatic illustration of that wavelength-dependent contrast. The second way to control path length is spatial. And you learned about spatial frequency domain imaging. That's the Fourier, that's the image transform in the Fourier domain of an experiment like this, where you take an optical fiber, put it in one point, and then if you have detector fibers that are put serially away, that are moved, and we look at the reflectance as a function of separation of those fibers, the fiber that's closest to the source will be looking at more superficial tissue structures. Those are the most probable paths to be detected by this detector fiber, as opposed to if we have a detector that's further away from the source, then that fiber or that detector is able to see more deeply propagating photons. So if we just look at, and this of course comes from a virtual photonics simulation, if you look at the reflectance as a function of source detector separation, we see very different behavior in the region close to the source, where close to the source, because scattering lengths are very short and absorption lengths are quite large, we see a scatter-dominated attenuation behavior, and further away from the source, we see a combination of scattering and absorption-dominated behavior. And we can take a combination of information from these two and deduce what the path length is, or the absorption and the scattering components of the tissue. So the important thing to keep in mind here is just coming back to what are the fundamental physical properties that are allowing us to see this different behavior. It's that absorption lengths in tissue in the near infrared are on the order of 10 centimeters, while scattering lengths are 20 to 40 microns. So that's a really, really different spatial scale. And I'm going to show you another example of a personal example of what I'm talking about. So here I am again. This is blue light. You see all the contrast. This is near infrared light. And if we just, and these are taken at zero frequency, just planar illumination, no structure. But here's a picture of me at higher frequency. It's still near infrared light. Higher frequency. We've changed the sensitivity map of the image. By going to higher frequency, we're making the near infrared light look a little bit more like blue light, we're starting to see contrast that comes from more superficial structures. And if you keep going up in frequency, you get more and more scatter-dominated behavior because close to the source, you're looking primarily at scattering interactions. So this is kind of an intermediate frequency. And if I just toggle back and forth, you can see very different contrast from these two images. So combined, you can get information from different depths. So the third major way to control path length is in time. So remember, if the scattering lengths are 20 to 40 microns, then we can calculate a scattering relaxation time. So you take that length and you divide it by the velocity of light, and that's the time. So that's a fraction of a picosecond in terms of a scattering relaxation time. And if you take that 10 centimeters and you divide that by the velocity of light, then you get an absorption relaxation time. And that's a fraction of a nanosecond. Now, I know a fraction of a nanosecond or a nanosecond sounds fast, but in the spectroscopy point of view, that's actually pretty slow. So half a nanosecond is slow. Fraction of a picosecond, well, that's pretty fast. But with spectroscopic techniques, it's possible to resolve these processes in time. So if you take a short laser pulse on the order of a few picoseconds, and you launch that into tissue, and you measure it some distance away, you'll see dispersion in that pulse. It will spread out in time. Just like we saw, there's a spatial dispersion, there is a temporal dispersion. And that's because the photons in the pulse are propagating over great distances. They're still moving at the velocity of light, but that pulse packet will have to necessarily spread out because some photons will go deep, some will be more superficial, and then when you measure the pulse profile at some distance away from the source, it will be spreading out in time. And the early arriving photons are more scatter-dominated. They haven't traveled that far, so they're more influenced by scattering processes. And the later arriving photons are more dominated. They're more likely to encounter absorbers. So this is the way, by measuring the entire temporal point spread function, one can separate absorption from scattering by comparing to a suitable model that would model the dispersion of a pulse. And this is just a cartoon illustration that shows that the more early arriving photons are interrogating more superficial structures, and the deeper propagating photons, they're arriving at a later time, and they're allowing you to see more deep structures in tissue. And so this is an approach that's widely used in our field. So this is kind of a summary of all of these concepts. We work in either the real domain, where you can take this input function in time and measure an output function where we're looking at the dispersion of a pulse. Or in space, we can take a point of light in space, just like this laser that's sort of overwhelming the field of view that I'm pointing up there. And we can look at how it spreads out in space. We can measure that with individual fiber optics as we're working in the real domain. Or if we work in the frequency domain, then we can take a sinusoidal input in time. So that's the Fourier transform of a pulse. If we want to capture all the frequencies in the pulse, then we would change the sinusoidal input to multiple frequencies. And then the output would be a wave that's attenuated or damped, and also the phase will be shifted from this input function. And the same thing can be said in the frequency domain for a spatially resolved experiment, where you put a sinusoidally modulated pattern of light onto tissue. And then it's possible to look at the output, the change in the sinusoidal modulation. You can look at a phase shift at a given frequency, and you can look at multiple frequencies. So in both of these techniques, looking at phase and amplitude as a function of frequency are critical components that allow you to recover all the information content. And what they're doing is they're approximating all of the information content that's available in the real domain experiment. You know that if your pulse is short enough, it contains all frequency components. In the frequency domain, what you can do is select the frequency components that you want, so you have just enough to be able to resolve absorption from scattering. And that applies both to the temporal frequency domain experiment as well as the spatial frequency domain experiment. So what I'll do, and you've heard about spatial frequency domain, I'll talk today about temporal frequency. All the spatial frequency domain conceptual framework and technologies and everything came from the temporal frequency domain. So I'll talk about all of these. One of the unique sort of distinguishing features between these two approaches is the sensitivity map. Where does the information content come from? In the spatial frequency domain experiments, you're in a non-contact imaging geometry. For the most part, most of your signal is coming from about 5 millimeters or so within tissue in skin. Depending upon the type of tissue, you may be able to probe a little bit deeper, but you're limited because you've got a planar geometry, you've got a limited sensitivity of your cameras. In the temporal frequency domain, because of the way that we have probes that are contacting the tissue, a source and a detector in contact with the tissue, you can probe several centimeters. If it's in reflectance geometry, you're typically looking at about a couple of centimeters deep into tissue, depending upon what your source detector separation is. If you're in a transmission geometry, because you can just put light into one side of your head and pick it up on the other side if you have a very sensitive detector, or what's more commonly done, people are frequently putting light into one side of breast tissue and looking at the other side. You can do this, of course, with a flashlight in your hand. You can completely transilluminate your hand and detect lots of light that comes through. So you're looking at very quite large depths, potentially, when you put probes in contact with the tissue. So any questions so far before Vasan really wanted you to get more serious frequency domain concepts? So I'm about to, this is a little preparation for, we're going to get a deeper before we pull back and you can get entertained by more interesting physiology. Yes?
For posterity. So two questions, actually. So first, when talking about using time to modulate your wavelength, it seems like when we're dealing with really short pulses on like the 20 picosecond scale, then there would be a limit to how far away you can look. Is that appreciable, or is that limited by other things first?
That's a good question.
You only get so many photons in such a short time.
Yeah, no, that's always a big challenge. So the practical response of detectors is always a big challenge. We're really always detector limited. So what people often do is a technique called time-correlated single photon counting. So they measure single photons. And that's a great technique for being super sensitive, but you don't necessarily have a tremendous dynamic range. If you want to look close to the source and far away from the source, all at the same time, you can have difficulty. So for sure, there is another practical disadvantage of that approach, and that is you really need to recover the temporal point spread function that's undergoing dispersion and do a convolution with some sort of a source function. And mathematically, convolutions are a little bit more difficult than working in the frequency domain, where you can do a subtraction or a ratio of phase and amplitude. But both techniques are absolutely equivalent. There will be times, so time-correlated single photon counting happens to be a really good way for looking at very deep tissues. But you don't necessarily need to do that if you've got lots of signal, for example. So there are pluses and minuses to each.
Okay, and then the other question, you had mentioned using just a few spatial frequencies or temporal frequencies rather than a whole range.
That's right.
I noticed mathematically you're still having Fourier transforms over there. Do you ever look at like a Fourier series decomposition, because it might be a lot easier to calculate for the type of input that you're looking at?
Yeah, I think a lot depends on your instrumentation. There are a lot of practical issues about the instrumentation, and we'll start to get into a little bit more of that will determine precisely how many frequencies you use and sort of the mathematical approaches to analyze the data. But there is a lot of, I think what you're pointing out, which is interesting and nice, there's a lot of flexibility. So if you have instruments that can do multiple frequencies, you could take one or you could take many. You can analyze them in different ways. The way you do referencing is much simpler than in the time domain, and it's less sensitive to making sure that you've got precise reconstruction of the input temporal point spread function. So you'll see, I think, this will maybe begin to emerge.
Great, thanks.
Yeah.
So you briefly mentioned that in the time domain that the sensors and the light source are in contact with the tissue. Does that have to be the case?
It doesn't have to be. No. Just in general, the way sort of many of these probes are constructed, the source and detector are in contact with the tissue. However, there certainly is lifetime or temporal-based imaging that can be done in a non-contact mode. Most of that has been done with intensified CCD cameras so that you can gate after a pulse or a sinusoidally modulated wave and measure if it's in the frequency domain. You can measure phase and amplitude in every pixel. But you will be limited in your sensitivity map if you have a planar geometry because I think you need to convince yourselves by doing some simulations in virtual photonics that you just don't have enough information content from those deep photons when you're doing a wide field illumination. You can do transmission, and that forces you to look at light that's propagated entirely through the tissue. And then you can use the time gating or the frequency gating to look at different propagation times and then look at different distances or sections of the tissue by sectioning through in time. But that involves, to really accurately localize that information, involves solving an inverse tomographic problem, which is complicated and not always well understood. Generally, that works best when you have some constraints. So if you have another imaging approach that you can use as an anatomic imaging constraint, so you don't have to solve for all of the unknowns, the size of the inhomogeneity, the depth of the inhomogeneity, the properties of it. If you can constrain it in some way, as in any imaging problem, then it can help. Yeah. Okay, so now we're going to move into a little bit more detail in photon density waves. So temporal frequency domain, sort of to come in a little bit of a closer view, we've got a source that we're intensity modulating in time. And when that is launched into tissue, the photons that are in this wave are undergoing multiple light scattering. So what was a wave that you can imagine is propagating with a carrier frequency before it goes in. So let's say we're modulating the light at 100 megahertz or 200 megahertz. When it goes into the tissue, then that wave is maintained, its structure is maintained, but the photons in the wave are scattering multiply. So the wave will start to spread out in space and time. And that spreading is a consequence of the tissue driving dispersion of the wave. So there'll be damping of the wave, which changes the amplitude of the wave, and there'll be a slowing of the phase velocity of that wave. The photons, the velocity of the photons are the particles in the wave, because now we're talking about particles that are being carried along by a density wave. So the particles in the wave are still moving at the velocity of light, but the wave itself has a phase velocity that's quite different from the velocity of light. And that's what enables these measurements to take place. So this is the wave, this overdamped, and it's actually an overdamped spherical wave as it propagates into tissue. And it's being attenuated at some rate per modulation wavelength. And that modulation wavelength is quite different than the modulation wavelength outside the tissue, because the photons in the wave are being scattered multiply. So they're changing the spatial features of that wave. And that's just a really fancy way of saying if I take a light point source and I look at it, it spreads out. It spreads out. But if I introduce temporal modulation to it, it still spreads out. It's just that I can capture the velocity of that temporally modulated component. So how do I capture it? Well, I have to have a reference function, and then I have detected light, and I measure the phase lag and the demodulation amplitude, and I can do that as a function of frequency. And what we typically use, so these are all model-based techniques, and you guys wouldn't be here if you were not interested in model-based techniques. So we use models in order to extract, I mean, it's one thing to measure the phase and the amplitude, but what does it all mean? So how do we assign meaning to it? Well, sort of in the simplest way, we use in the diffusion, in the scatter-dominated region, we use a diffusion equation, which you're familiar with now. And so broadly speaking, we're looking at the fluence rate as a function of space and time, a build-up term, which is telling us about the scattering, which is lossless from the light. Just imagine if there's no absorber in the tissue, the light will just keep bouncing around forever, and that wave will just keep spreading out. If it's a pulse, it'll just spread out infinitely in time until you put some absorber in, and then it will limit the paths. It will suck up some of the light, and it will change that temporal point spread function. And so here's the loss term. And then we have a photon diffusion coefficient, which is a function of the absorption length and the scattering length in tissue. And in order to make this work for frequency domain photon migration, we actually have to solve this in terms of a modulated fluence rate. And in our case, we typically employ sinusoidally modulated light sources. So the modulated fluence rate has both a DC and an AC component to it, as we know from how we describe waves, sinusoidally modulated waves. And this is the solution in infinite medium. There's a nice treatment of this for the boundary conditions that we encounter in tissue, where we've described a variety of different boundary condition phenomena and boundary condition approaches. It's, of course, makes it way more complicated, but those boundary conditions are actually what we use every day in the calculation of optical properties in our instrument, because unfortunately humans aren't infinite media, but we can approximate them as semi-infinite media. So we use a semi-infinite diffusion approximation in order to fit all of the data that we acquire from human subjects. And you would employ other boundary conditions if you were looking at a transmission geometry, and you can apply a variety of approaches if you have irregular tissue structures and so forth. And a lot of that is contained in this paper. So in infinite medium, and this will hold true for any boundary condition, so this is the basic functional form, we can describe the AC component of the source as having real and imaginary components. So what we see then, if we expand this, we see that there is a complex wave with real and imaginary components associated with this photon density wave, as you can really describe any wave in terms of a complex number. This is not an electromagnetic wave per se. It's a damped scalar wave, but it still has all of these characteristics of waves that we depend on and can describe mathematically. And that's what makes it kind of intriguing. So we can go a step further, and we can look at, just like any wave, we can look at the dispersion relations of this particular type of wave, a damped photon density wave. And that's how we can gain a better understanding of the type of instrumentation that we need to use in order to be able to quantitatively separate absorption from scattering and characterize a tissue. So this is an example of dispersion of a photon density wave in a tissue of these. I just have a simulation for these optical properties. Low absorption, sort of typical scattering that we might encounter in a tissue, 1 per millimeter, refractive index of 1.4. And on the y-axis, we have frequency, omega. And on the x-axis, we have k, wave number. And what you're seeing is a separation of ki and kr, the imaginary component of the complex wave number, and the real component, Ki and Kr. And the first thing that you can sort of appreciate is that at low frequencies, what we have is the phase velocity. Phase velocity, just to sort of remind those of you who haven't been thinking about waves in a while, phase velocity is equal to omega over k. And for convention here, we're going to say that Ki is giving the information on phase, and Kr is going to give information on amplitude. So if we look at omega over k, we see that it's actually independent of frequency at low frequencies. So what are those low frequencies? It's all sort of down here. Qualitatively, you can see that's down here. So you've got a linear plot down here. And then as you continue to go up in frequency, you start to see some nonlinearity. That nonlinearity is the dispersion of the wave. So if you think of that in terms of electromagnetic waves, you know, that would be, there would be some dispersion in index with frequency. But these aren't electromagnetic waves. These are density waves, scalar density waves, but they still illustrate the same type of dispersion behavior. So what is driving the dispersion? What is driving the dispersion is the loss relaxation time. So if we take the loss relaxation time, which is simply the absorption coefficient times the velocity of light, and we turn that into a frequency, in this case, the absorption coefficient is 0.006 per millimeter. The loss relaxation time corresponds to 200 megahertz. So that means at frequencies that are much less than 200 megahertz, then my phase measurement will just be linear with frequency. But at frequencies above 200 megahertz, if I can sample around or above 200 megahertz, I'll start to run into this nonlinear behavior. So with frequencies that are much less than velocity of light times the absorption coefficient, then phase velocity there is no frequency term in the phase velocity. It's just entirely linear. But if I have frequencies that are greater than the velocity of light times the absorption coefficient, then what we see is the phase velocity is dependent on frequency, and there is dispersion of the wave. And that's, in the frequency domain, a way of understanding and stating what frequencies do I need to measure in order to effectively separate absorption from scattering. If I have a temporal point spread function measurement, I really don't care because I've got a pulse, a couple picoseconds, and I measure the entire pulse, all of the dispersion of that pulse. That contains all the frequencies. But in the frequency domain, I can have a monochromatic experiment or a slightly polychromatic experiment by using several frequencies. But I just need to sample somewhere around here where the dispersion is in order to be able to separate absorption from scattering. What's interesting here, if I look at the real part of this wave, is that it is fixed, it drops off with frequency. So when I hit a limiting frequency, the AC component of the wave, which is 1 over the penetration depth, is 1 over Kr. So at low frequencies, 1 over Kr collapses to the DC penetration depth. So it just looks like a DC light source going into the tissue. But as I increase the frequency, the penetration depth is gradually diminished. So that's frequency sectioning of the tissue. Just like in the spatial frequency image I showed you of the high frequency picture of me, you saw more contrast from superficial structures. If I modulate the light in time at higher frequencies, my penetration depth is 1 over Kr, so my penetration depth will actually decrease. If I go to high enough frequencies, I'll only be looking at superficial structures. So this mathematical behavior allows us to predict where the wave is penetrating in depth in the tissue. Now, most of the time, we're working just around this dispersion regime, so where we start to begin to see some nonlinearity, and the DC penetration depth and the AC penetration depth are quite comparable. But if we can go up to high enough frequencies, we can actually separate those two. So the other really interesting thing about these photon density waves is that the wavelength of the photon density wave changes. The scattering focuses the wave. So if there's no scattering, we're in air, you just modulate light at 200 megahertz, then your wavelength, your modulation wavelength is 9 meters. But with multiple light scattering at 200 megahertz, your wavelength, which is 2 pi over k, is going to be 10 centimeters. So quite a bit shorter. And that's a consequence of the multiple light scattering. So you can kind of think of this as a way of focusing of the wave. It's also a little bit like near-field optics. So we're measuring at not many wavelengths. So the actual wavelength is 10 centimeters. So we're not really typically looking 10 centimeters away from a source. We may have a source detector separation of a few centimeters. So we're kind of sampling these waves at a fraction of their wavelength. So by looking kind of at this roadmap, you get an idea of the best way to do an experiment in a tissue and what frequencies are needed in order to sample that dispersion. Yes?
So on the last slide, you said in the low frequency limit, we were at 16 millimeters per nanosecond. So if I'm right, then that is really fast, like 5% the speed of light fast.
That's actually really slow. It's slow.
In terms of detectors, does that cause any issues? Because
that's exactly. This is slow. The idea is we want to slow this propagation, you know, all this, we want to slow the light down. If we have to detect the phase velocity of the electromagnetic wave, then it's much more difficult. But because of multiple light scattering, and there's dispersion spreading out of the wave, it actually slows down to 1/10 or 100th of the velocity of light. And that's what allows us to measure the phase and the amplitude very, very effectively. You're right, if it doesn't slow down, we're in trouble. It's really hard to measure the phase and the amplitude. But because of the multiple scattering, and the more scattering it is, the slower the wave gets. And in dispersion, that's going to be a consequence of the frequency as well. Lawson.
I was wondering if you could give us a little bit more insight into the relative strengths and weaknesses or advantages of spatial modulated light versus the temporal modulation, because clearly, as you said, if you want to separate absorption from scattering or get sensitivity to both, you've got to be operating across this interface where you start to see dispersion in the K imaginary term, right? But clearly that modulation frequency is going to change dramatically if you have a change in absorption. And so that might have some impact as to the range of optical parameters or optical absorption parameters where this technique could be used advantageously. And then the other thing that strikes me when I see this plot is that the K real is actually quite low relative to your typical scattering coefficients in tissue, meaning that, and that relates to, I think, your penetration depth in some sense, or your ability to have minimal damping in some sense in the amplitude with distance. And
so I think maybe let me zero in on that, and this will become more clear. I have another slide. If you look at the functional form of Kr or the AC penetration depth, what you see is this is somewhat weakly dependent on modulation frequency. So you can probe over many frequencies in modulation in time and not dramatically impact your penetration depth. Whereas in spatial frequency domain, you change your frequencies, and you can have a huge impact on penetration depth. So that's both good and bad. I mean, if you understand the pluses and the minuses of that, you can really make it work for you. So what this allows you to do is sweep over many frequencies, and you can take advantage of the frequency-dependent dispersion to calculate absorption and scattering without dramatically altering your volumetric field of view with the contact probes. Whereas in the wide field spatial frequency domain imaging, if you scan over many frequencies, you're going to have very different sensitivities to depth, which gives you higher spatial resolution. So we've shown that you can use tomography in the spatial frequency domain. So solve an inverse scattering integral, do it entirely analytically. And we can get resolution that's a millimeter in diffuse optical tomography with spatial frequency domain imaging. And I hate to say it, but we've even seen better than a millimeter, although I don't want to reliably claim it. But it's kind of heretical to think, could you have, using analytical approaches with a diffuse wave, resolution in 3D tomography that's on the order of a millimeter? Yes, you can with spatial frequency domain, where you've got very nice depth sensitivity and inherent sectioning capability. And those are just with analytical models. Super fast solvers. But in the temporal frequency domain, you don't get that kind of fine resolution until you sample a pretty broad frequency range. And from an instrumentation point of view, although it is instrumentation that comes from telecom and those things are out there, it's harder to work with RF. It's harder to build those systems and get them to work reliably. So from a practical point of view, the spatial frequency domain is just a really great way to have broad access, because all you need is a spatial light modulator, which are widely available. And but the downside, of course, is if you want to really, on a routine basis, sample in deep tissue structures, it's not amenable to that.
So can you also comment on how maybe changes in absorption, so say you had 10 times more absorption, how that would impact
yeah, then you have to, then that just extends this linear region.
Right.
So you have 10 times higher absorption, you're going to have to go up in frequency in order to be able to sample that dispersion. And I think I can, maybe the next slide might bring that more into a practical view. So this is the practical view. That was all sort of the abstract theory. And now you can relax. And we're going to come back to what does a measurement look like. So what we measure the amplitude and the phase of that photon density wave. And we do that as a function of frequency. So these points are data that are acquired. And this is from a scattering medium. So then we fit the actual measured data, and that fitting is done to a model that comes from the diffusion approximation, as I was explaining before. Depending upon the boundary condition, it's probably a semi-infinite boundary condition. And that's the fit both to the amplitude and to the phase. And what you can see here is that if you look in this part of the curve, it's somewhat linear with frequency. So that's the region of non-dispersion. Those are the low frequencies. And then as we go higher and higher, we start to see this curve. And from a practical point of view, for those of you who do model fits, if you have a nonlinear model and you got data, if your data is not nonlinear, you're not going to recover your free parameters. So these are nonlinear models. We need to have nonlinear data in order to adequately and unambiguously recover the free parameters. And what are the free parameters? Two things we're interested in: absorption and scattering. So to really unambiguously get the absorption and scattering separated, we've got to have some nonlinearity in the data. And we benefit from having complementary, we have everything about the wave. So the full way, the complete way to describe the wave is the phase and the amplitude. So now you could actually get it from one of these alone if you have sufficient nonlinearity. But we like to have them both. We like to have a super redundant system. And additional redundancies in our system are coming from what we do. This is for a single laser diode, a single wavelength. And then we'll have multiple wavelengths. So we'll calculate the mu sub s prime at these multiple laser diode spots, and mu sub a, the absorption coefficient, at multiple discrete optical wavelengths. Carol. This one?
Yeah.
The photon density wave map,
yes,
roadmap?
That one. So I was trying to think of it kind of in a Monte Carlo way. And I think, because you were saying there's this linear part and then it goes nonlinear and you want that nonlinear information. But I was thinking of the distance, the mu a is telling you the distance between, 1 over that is your average distance between the time that you hit your first absorbing event. Mm-hmm. And so you need to have your modulation frequency shorter than that distance in order to capture that. If it's too big, you're gonna go over it in a sense. And
yes.
So that's kind of what that plot is saying?
Exactly.
Okay.
Yeah.
Great.
Yeah, and there's another really interesting feature that's sort of related to that, is that at the same time, this wave, it's an overdamped spherical wave, so the rate of damping is also something that you're fighting. So if there's if the 1 over E damping rate is, in this case, it's 27 dB per modulation wavelength. So you're fighting that 1 over E damping. The amplitude of the wave is diminishing every modulation wavelength. So you've got to have multiple scattering to focus those waves, but that limits the distance over which you can accurately measure the phase and the amplitude. So you're kind of balancing all of that. But in the end, all you have to worry about is, did I get enough phase and amplitude signal to make this work so I can see some nonlinearity? So, yes?
On that previous slide.
Yes.
Sean, of course, sorry. So, sorry, one slide after this. There we go. I'm sorry if I missed this, but what exactly are you fitting to that data? I mean, you're fitting some functions on there, but without knowing exactly what you're fitting, then it's hard to tell where we're going to get mu-s.
So,
okay.
So this is the infinite medium expression. And then you can do more math, and eventually you can get an expression that says phase is equal to, and amplitude is equal to. And in all of that are going to be your free parameters, absorption and scattering.
Okay.
Yeah. And you want to do that for the appropriate boundary condition. So, and that's all in all these papers. So the final distilled expression. But what also all those papers show is how we got to that expression. And these papers, even if you go back, I believe in the first paper that I wrote on this, which was just properties of photon density waves, I talk about how you can sort of even very simply use the diffusion approximation. So why is that even any good? And what assumptions you have to make about the transport equation. So if you kind of go back in time a little bit, you can capture a little of the rationale. Because again, from a historical perspective, I told you about now we are in this time where people are buying medical devices and they all have biophotonics in them. And in the early 90s, people would tell me that it's impossible to measure things in deep tissue. Study sections would say, how can you be proposing to measure cancer deep in breast tissue? That's impossible. Everyone knows light doesn't go into tissue. So it wasn't completely obvious all the time that you can use light to measure centimeter deep structures in tissue, much less control it in any kind of way. And probably even now, you'll find physicians that will just say, wow, we know light doesn't go into tissue. That's impossible. So, so these are our discrete calculations of absorption at these discrete wavelengths and scattering at these discrete wavelengths. And so you know this functional form of the power law for scattering, and this comes from me theory. And this is a pretty good descriptor of the wavelength dependence of scattering. So we've got a prefactor A and a scatter power or slope B. And if we just fit these measured dots to this me theory expression, you can recover the A and the B parameters. So that's a very general expression that many people use, widely used in the field. Interestingly, we use this now as a constraint for yet another inverse problem, which I'll show you in just a second. So this is a powerful potential constraint. So we take this, we recover the A and the B parameters for those 4 discrete wavelengths, and then we combine that with broadband reflectance spectra. So if I just have a white light source, a broadband source, and shine it on tissue and I get the reflectance spectra, you'll see dips. So anybody know what this dip is over here? That's deoxyhemoglobin. There's a nice absorption feature at about 780 or so that deoxyhemoglobin corresponds to. Anybody know what this dip is over here? Water. And you can read this dip, lipid. So there's some really great features that you can see just from reflectance. But reflectance is a combination of absorption and scattering. But we actually just figured out the scattering here with frequency domain techniques. So if we combine that and that, mathematically, what's left? Absorption. So absorption is what's left. So then we can recover the full absorption spectrum. And now you can see quantitatively the water absorption exactly, or the region where there's water absorption, the region where there's lipid absorption. You see the very nice deoxyhemoglobin slope here and peak over here. And these are absolute values. So any reflectance measurement is a combination of absorption and scattering. We quantitatively measured absorption and scattering at a few discrete wavelengths, and then combine that with a qualitative measurement of reflectance over 1,000 wavelengths. I mean, just take your pick. You can measure it over a narrow band or a very broad band. You just need to recover this functional form. And that's an example of a constraint. And in our field, many people use constraints in a variety of different ways. In tomographic imaging, a common constraint is to use a conventional medical image, like an ultrasound image, or an X-ray, or an MR. And then you can say, well, I know the depth of my tumor, I know the spatial extent, and then you can apply diffuse optical tomography algorithms, which will then improve your ability to estimate the concentration and the functional aspects of what's inside. So that's kind of the next level of inverse problem, which is a simple linear fitting. Now we can use Beer's law, and we have all of our chromophores that we're interested in. Well, these aren't all of them. There's more subtlety and complexity to this, but these are sort of the main ones. And with this measured tissue spectrum, you can fit and determine the concentrations of all of these components. So that's basically how we do our temporal frequency domain, as well as time-independent diffuse optical spectroscopies. It's a combination, it's a multimodality approach that typically integrates the two. Now, we don't have to always do the broadband spectroscopy. We can still do hemoglobin oximetry just with those temporally modulated sources. Or we can just use time-independent information content and do ratiometric measurements. And there's $1 billion a year market to do that in pulse oximetry and tissue oximetry. Those are all CW time-independent methods that use just a few wavelengths. And they typically use a very well-validated and well-understood endpoint, which is tissue oxygenation. So here's the evolution, in some sense, of the technologies. I started doing this in the early 90s, and this is only a small fraction of the whole room with a giant optical table with RF synthesizers and big lasers and, you know, expensive photomultiplier tubes, a Optical cell for modulating the light externally, which only a few of us could actually align, and I had to climb up on the table to align the laser beam with respect to the Optical cell. Not a very easy instrument, but everything that instrument does, or did, we had an argon dye laser, so it could tune all the optical wavelengths. We had a Optical cell. We could look at a lot of different frequencies. Everything that we did in 1991 is the same as we do today. It just took a lot longer, and it was more expensive to feed. So we went to a network analyzer-based instrument, which we could put on a cart. And a network analyzer, it provides an RF swept source and phase lock loop analysis, so you can measure phase and amplitude. The RF source, there's like a 20 dBm RF output on that, so there's plenty of power to drive laser diodes. And it's actually a very nice off-the-shelf way to do this. And eventually we built this into kind of a more portable cart and yet more portable carts. And over time, with students and postdocs, we've been able to replace the network analyzer and have a board-based instrument. And so there are 4 lasers. You're going to see this later this afternoon that are in here. And this little tiny box, which is about the size of an external hard drive, does all of the RF generation and detection, and there's also a spectrometer and a white light source in that, and that's portable. And that's actually the same box that I brought to visit Jeremy in Côte d'Ivoire. So that's sort of what it looks like. There are various probe geometries that you can use. This probe has an avalanche photodiode detector in it, which you'll see. It also has fibers that are bundled for delivering the intensity modulated laser diodes, as well as the broadband source and a fiber for picking up the broadband light and sending it to a spectrometer. But probe design is really important in our field. The interface between an instrument and the patient can make the difference between whether or not you get the right information or you're just forever fated never to get your experiment done. So we do a lot of probe design, think a lot about that. Okay, so now I'm going to switch gears and just show you some examples of this type of technology working and what it can be good for. And a lot of what we're obsessed about is oxygen metabolism. And this is the big picture. This is my very big picture of biology. This explains all of biology, maybe. So it's kind of a balance between supply and demand that we're really interested in understanding. And we know at the arterial side that oxygen supply is provided in arteries and arterioles, and that oxygen tension is at its highest, closest to the source. But there's this gradient as we move from the source to the site of oxygen consumption. And the end point of oxygen consumption is going to be the mitochondria inside of a cell. This is where oxygen consumption is taking place on a regular basis to make ATP. So a fuel, glucose, is combusted with oxygen in order to produce ATP. And normally that's going under a process I think you're all familiar with called oxidative phosphorylation. So that's typically going pretty smoothly. You're making a lot of ATP. If you're in a well-balanced system, then whenever there's an increase in the demand here, then there's an increase in the supply. And people in neuroscience call this neurovascular coupling. You're thinking, you're moving your fingers, and your neurons are being activated. Your brain doesn't want to become hypoxic because those neurons are sucking up oxygen. So there's vasodilation, increased blood flow. There's a change in the supply to meet that demand. So the supply and the demand are well balanced. And that's an example in the brain, but same example for any part of your body where cells are consuming oxygen. Various diseases over time can impact either the utilization of oxygen, so mitochondrial diseases, generation of free radicals. In this combustion process, it's not unlikely that free radicals will be generated, and those free radicals can damage mitochondria and other components of the cell, impacting the ability of the cell to consume oxygen and perform other functions. So those would be incomplete or partial consequence of combustion. I like to think of it as, you know, if you've got a fireplace and you're burning really good fuel, you get really wonderful heat and great combustion. But if maybe the wood is wet or there are impurities, it starts smoking. And the smoke you can think of as free radical generation. That's not very good combustion. We want good, clean combustion wherever we can get it. Now, you can also have damage to the supply side, the vascular side. And these things kind of can go hand in hand. So the vascular side, you can have alterations in vascular structure that are a hallmark of peripheral arterial disease or coronary artery disease, endothelial dysfunction. You can have increased rigidity in the vascular structures due to continued alterations in the extracellular matrix of blood vessels. So cross-linking of collagen, for example, it increases rigidity. It increases peripheral vascular resistance. So when there's a demand, the supply can't react adequately. And that can lead to chronic alterations in the tissue metabolism itself. And all these things are detectable with our technologies, with our field. So one example I want to give you is this is something that we didn't do this work. This is another group that I think is kind of interesting, seeing what they've done. And they're not optics people, and they're not worried about making quantitative measurements. They just took an off-the-shelf Medtronic, Covidian, INVOS tissue oximeter, and they put it on 1,200 patients who were about to undergo cardiac bypass surgery. And they measured their brain oxygenation before bypass surgery. So commercial instrument measured 1,200 people's brain oxygenation, and then they did the ultimate outcome measurement. These are called survival curves. So they looked to see how long were these people still alive after the surgery, after bypass surgery. And the interesting thing that they found is that if you look at the total population, if your brain oxygenation before you even went into surgery was less than 50%, then you had a 25% greater chance of death at 1 year. So that's predicting the future for somebody just with a simple, off-the-shelf tissue oxygenation measurement of your brain. And for the high-risk group, that's a special category, and those high-risk identifiers were related to things like, diabetes and smoking and other factors, comorbidities. Then if your saturation level was less than 50%, you only had a 45% rate of survival at 1 year. So even worse. So just from kind of assessing people before surgery and looking at their habits, you could determine whether or not they were a good candidate for surgery. So I'm just waiting until the legal community kind of gets a hold of these types of studies, because you can imagine maybe it should be a requirement to measure everybody's brain oxygenation before any extended surgery. And imagine if we had more accurate instrumentation. So this is a plus minus, this is just a 50% cutoff. What if you're 54%? Or 57%? What if we had really good quantitative measurements where we could compare individuals very, very accurately? So that could be pretty impactful. And we've done work ourselves, not looking just before surgery, but what's going on with your brain during surgery. So this is a commercial frequency domain tissue oximeter. And here we're looking at 2 different pressure agents. So as soon as you go under anesthesia, your blood pressure drops, and the anesthesiologist gives you a vasopressor in order to increase your peripheral vascular resistance and increase your central pressure, your mean arterial pressure. And if you look at phenylephrine, which is one type of pressor agent, versus ephedrine, you see in both cases, after the bolus, you get an increase in mean arterial pressure. But in the case of phenylephrine, you actually see a drop with every injection of this bolus in brain tissue oxygenation. This is taken from prefrontal cortex, whereas in the ephedrine, there's no change. And the implication of this is that with the phenylephrine, you actually see a rapid rise in the mean arterial pressure. And this appears to be correlated with a drop in saturation. And other people have shown, actually lots of studies in literature have shown that when your brain oxygenation drops frequently during surgery, that there can be cognitive impairment. It's called postoperative cognitive decline, and it's a pretty well-known phenomenon. So what we're seeing now is increased attention to not only measuring people perhaps before surgery, but use tissue oxygenation as a measure during surgery to see both what's the impact of pressor agents and other interventions to ensure that patients aren't having significant drops in brain oxygenation that could lead to brain damage. And again, the legal community is just waking up to this, and so this is going to be a really big growth area. So we spent a lot of time on photon density waves, and I have some examples. You know, what I might do is I'll skip over a couple of these. Yeah. Yeah. So what I'll do is I'll just show 2 examples, 2 more examples now that we've covered the brain. This is a pretty interesting new work that we've done where using DOSI and the full capabilities to measure oxy and deoxyhemoglobin, water, and lipid, we asked the question, how could we get involved in and understand better metabolic syndromes? Could we figure out how to use this technology in heart disease and prevention of disease and diabetes? So one of the sort of hot areas right now is understanding lipid metabolism. And we have a lot of lipid around the abdomen that's available for measurement. And many people think that that's just, you know, just dead stuff. It's not really very active. But increasingly over the last several years, people have shown that there is metabolic activity in subcutaneous lipid as well as visceral fat. And its activity is really important. And in fact, if you don't have subcutaneous fat to store your fat, you'll start to accumulate fat viscerally, which is really bad. So you want to have healthy subcutaneous fat. You don't want too much of it. If you have too much of it, then it promotes insulin resistance and leptin resistance. Insulin, of course, is important for regulating your risk of becoming a diabetic. Leptin, has anybody heard of leptin? That's another hormone that controls your appetite. So you can develop significant resistance to this hormone that's telling you to stop eating, that you feel full. And then you just keep eating more, and so it just contributes to this cycle of obesity. So what you really want to do, and what will happen if you go on a diet and you exercise, is you minimize your lipid burden. You shrink your adipocytes, and you minimize your adipose tissue burden. So we asked the question whether or not DOSI, the spectroscopic mapping and imaging, could detect structural and functional changes in adipose tissue. And we looked at 10 patients who were on a 12-week calorie-restricted diet. And this is all working with Dr. Malik, who's the director of our preventative cardiology center, the Samueli Center. So here's an example of one of the patients. So we have ultrasounds on everybody. And you know, with ultrasound, you can see that there's a fat layer. That's about all that you can tell. There's a nice subcutaneous fat layer. But optically, what you see is this very beautiful wavelength dependence of scattering. And we were pretty surprised to see that 6 weeks into the diet, that the scattering spectra changed quite dramatically. There was an increase in scattering and a change in slope. And the same thing is going on for the absorption spectra. So here's the baseline. You see the water to lipid ratio. Here's 6 weeks in the diet. There's a shift in the water to lipid ratio and a change in this deoxyhemoglobin feature. So those are mapping those people, following them over time in this calorie-restricted diet. And then, of course, since we're doing mapping, we can generate images. So here's an image of a patient at baseline 3 months later, where we're mapping the A parameter in the scattering. And here is the water content mapped. And you see dramatically increased water content. Now, of course, you can't see that with your eye. That's reporting only on the subcutaneous lipid structure. So what's going on? Why is there an increase in scattering and a change in slope? That's reflective, as you know, your calculations, what you're doing. I mean, this is why computation is important. You can deduce from that what's going on the microscopic scale. And how do we reconcile that with the physiology? So what we believe is going on is that from a mathematical point of view, we've got smaller, denser particles. So that's unambiguous from the math. What is the physiology that's consistent with that? So what we speculate is that there's adipocyte shrinkage. So the adipocytes actually shrink. They get closer together. There's activation of mitochondria because there's metabolism going on in the fat now, and we're picking that up. So the discontinuities between refractive indices are getting closer and closer together, causing that higher scattering and the steeper slope, and the mitochondria are becoming activated. And where do we come up with that explanation? Well, people who do fat biology have found this by doing biopsies of fat and analyzing them under the microscope and doing molecular studies of fat. So all of this stuff is going on in parallel in biology labs with animal models. The human subjects, of course, don't want you to drill a hole into their subcutaneous lipid and make those measurements. But optically, we're actually reporting on that. So we see perfusion and alteration in scattering structure. So an interesting way to be super sensitive, potentially, to kind of a new endpoint. We're also similar approaches in breast cancer, and in fact our breast cancer work is what really inspired confidence that we could go ahead and map your abdomen, which has a lot of subcutaneous lipid, and get that kind of information. The two major questions that we're sort of asking in breast cancer is a tumor malignant or benign, and is it responding to chemotherapy? And the idea is that we can take the probe, and when we encounter a subsurface inhomogeneity, then the spectra will change. We have absorption spectra, we have scattering spectra, and if there's something buried beneath the surface, then we're going to see a big alteration. And here's an example of that. So here are maps of a patient where we can measure the full spectra, and then we can calculate all the different components. Here's oxyhemoglobin, deoxyhemoglobin, water content, and lipid content, all from a subsurface tumor. This is about a 2 to 3 centimeter mass, invasive ductal carcinoma, buried about 1 centimeter beneath the surface. It's palpable, it's a large mass. We're not trying to find something very small. We're trying to characterize something pretty big. And then we can combine some of these into an index. This is deoxyhemoglobin times water divided by lipid, which is a very nice high contrast function. And you can see contrast can be 5, 6, 7-fold between the tumor and the surrounding tissue. So there's a lot of blood there. There's a lot of water. Water extravasates from the vasculature. It gets sequestered in the extravascular, extracellular space. MRI, X-ray, and ultrasound all use water as their principal form of contrast. So the fact that we see more water is not surprising. It's just that none of those techniques are quantitatively measuring the water, the lipid, and the blood content. So we're able to recover that information. And then if you take a patient who's going through chemotherapy, and this is called pre-surgical neoadjuvant chemotherapy. Chemotherapy designed to shrink a tumor before surgery. That can potentially improve outcomes if you can get a complete response. So here's a baseline for a patient. Here is early therapy. This is about 1 week, mid-therapy and post-therapy. This is a non-responder, and you see the tumor effectively, although actually it is changing, it's not changing as much. And if we take this case study of this 52-year-old, this is a perimenopausal patient, a 2-centimeter tumor, triple negative is the molecular subtype. Here's the map. You actually do see areolar metabolism combined with the tumor metabolism. This is the baseline. Here's the ultrasound. So you can see a very nice delineation of the tumor. This is a hypoechoic region. Lots of water there. Here's dynamic contrast enhanced MRI. So we have multiple modalities that we can look at this. And here is a week for this patient. And we already see a change in the DOSI image. This is the ultrasound image, and there is no change in the size of the tumor from ultrasound. So this is the strength of optical methods. They're functional. We can look at changes in metabolic rate of oxygen consumption. We can look at changes in perfusion, and we can see those before there are anatomic or size changes that are detectable with other modalities. And we can extend this to entire breast imaging and potentially look at tamoxifen or other types of agents that could change your breast density and your risk. So this is an entire breast scan, and these are just different contrast elements that are shown from the water to the oxyhemoglobin, the deoxyhemoglobin. So you can visualize these in different ways. We have fun with this. This is actually generated with Xbox Connect. So just using one of the time-of-flight cameras that come from Xbox is a way of generating the 3D topography. And then you can fuse that with the 2D maps, and you get a very nice, physicians really like that way of seeing things, as opposed to just a dot or a line scan or something like that. So representation of this in an image. And here's an example of a patient who we measured 1 year later. So here's that patient's image of lipid at baseline. Here is their lipid map 12 months after taking tamoxifen. So this really underscores one of the strengths of the approach, because it's quantitative, where we separate absorption from scattering. We have absolute measurements. You can follow people over time. You can take the probe off and put it back on. You can follow many, many people and compare different individuals. And so that's different from the qualitative measurements that are primarily trend measurements that you get with current medical oximetry devices. Those are fantastic. You put them on, and then you put the patient in surgery, and you follow their brain oxygenation. It can go up and down. But that's not an absolute measurement. That could be different if that patient comes back again, or you want to follow them the next day, or you want to compare that person to another person. And that's why in that first study I showed you, they picked one number as a cutoff, and it's a pretty drastic number, 50%, because they don't have the fine resolution to be able to compare people who are 53, 57, 62. You know, 50% is just a very nice broad number looking at two large populations. But with quantitative techniques, potentially, you can have finer resolution and do a better job of predicting outcomes. So that's really the summary of all of this. We can image drug and radiation therapy with these approaches, help facilitate some surgical guidance. Surgical guidance particularly is powerful, I think, in non-contact imaging mode. Predict risk and outcome. Ideally, we'd like to be able to measure something about people and predict their future. Just like in that brain imaging study where they predicted the outcome of patients from bypass surgery. And these methods are easily integrated with multiple modalities. Where are things going? Of course, you can miniaturize even further. You could potentially wear these types of sensors. And this is compatible with the whole direction in healthcare, which is towards personalized medicine. Now, I think if you talk to the average person in medicine and say, what's personalized medicine? If you talk to Francis Collins, who's the head of the NIH, Francis Collins will say, genomics. Absolutely, genomics. And I think it's important that those of us from the engineering side of medicine kind of remind people and push back a little bit and remind people that genomics is not the only way to do personalized medicine. There's a lot of really beautiful sensing and imaging and technologies that can look at physiology downstream. So genes are important, of course, but they're not the whole story. A lot of stuff happens after gene expression, and that is primarily where medicine is practiced. So medicine is not really practiced at the genetic level. There are very few interventions, even if you knew everything about the genome, there are very few interventions that will directly reverse a disease because you've targeted the genome. There are a few, but not that many. So I think great opportunities for expanding the kind of things that we do by looking at perfusion and metabolism and composition using optical approaches. But here is where our biggest challenge is. You see, I tried to emphasize not only the measurements, but the outcome. So what does this measurement mean in terms of the future of the patient? And that's where our biggest challenge is. We have to do studies and really think through what is an outcome and how do we link an optical measurement to the outcome. That first study I showed you, well, survival, that's the ultimate outcome experiment. But you'd like to ideally have surrogates for survival. You don't want to have to wait years to sort of assess survival and your optical measurement. You want to have intermediate surrogates, and that requires really thoughtful approaches, multidisciplinary collaborations with clinicians to deeply understand what outcomes are they after and how do we quantify our measurements to capture them. So that's the whole thing. You guys have met a lot of these folks, perhaps in conferences and at the BLI, you'll meet more of them, and our funding agencies for all of our support. So I'm still awake and I could answer questions if you guys have some still. So thanks very much.
Questions for Bruce?
Robert.
Touching on your point of being able to make absolute measurements for a given patient over time, how can you tell that you're not, say, probing something that was already there but perhaps was deeper and scattered, and your light was scattered too much beforehand to be able to see it? In particular, I was thinking about that with the diet loss. So I think it was the water absorption or something like that. It was very, very tightly correlated to the above map. So it got me thinking how maybe that was a layer that was there underneath, but you weren't able to have that penetration.
That's a really good question, and I believe in the supplemental information. I don't remember if we put it in the supplemental information or not. A reviewer did ask that question on the paper. So we went through it's actually in the discussion of the paper, and there may be a supplementary figure on what you guys are doing. Monte Carlo simulations to assess the photon hitting density so that we could determine what fraction of the signal. So we had the ultrasounds from everybody. So we knew the layer thickness. And so we basically were able to determine what fraction of the signal is coming from the lipid and if there's any contribution from underlying muscle. And essentially the contribution from underlying muscle was zip, zero, not that much, very little. So that absolutely is a concern, because if the adipocyte layer or the adipose layer is shrinking, then for sure there could be contribution from a deeper layered structure that just has more water content to it. But we were happy to see, thanks to virtual photonics, that there was virtually no contribution from deeper layers. And that probe source detector separation was 2 centimeters, as opposed to our typical 3 centimeters for breast imaging, to further constrain the mean penetration depth. All those people had pretty big subcutaneous adipose layers, essentially semi-infinite media.
They were your infinite media subpopulation.
Yeah, effectively infinite. Yeah, that's a really good way. So that's how you can kind of go back and forth with simulation and measurements to sort of confirm what your sensitivity map is. Yeah.
So I guess this is more of a, not specific on this talk, but more of a general course question, but it's related to this. So the ultimate thing is you take some reflectance measurements, or you take some measurement, and you need to ultimately get back to clinical outcome or a measure of saturation or something. And then in that process, you go through this, you go through your measurement, you go through absorption and scattering, and then you try to get to your concentrations. Why do we need to go through that absorption scattering in between point? Because I look at this from a digital camera standpoint, and digital cameras, what you try to do is you try to relate what the sensor sees to what humans see.
Yes.
And there's one part where you could sort of try to estimate the reflectance functions and illuminate spectra in the scene, and then from that predict what the human sees and relate the two. But in that end, it's just a lot easier to just go, hey, this is what the camera got, and do a direct translation to what the human sees, and not actually go through that illuminant and reflectance thing. So why do we need to go through absorption and scattering coefficients? Well, that's an intermediate result,
Yeah.
and we want
Yeah.
a final result.
So I think the short answer is we don't necessarily need to do that. And it's going to depend on the application and what you're trying to accomplish. And I think that probably for most medical devices, so currently there are probably 30 or so FDA-cleared oximetry devices. None of them separate absorption from scattering. None of them use wavelengths other than oximetry wavelengths. So what's the near-term opportunity? The near-term opportunity is just to use the same approaches. They don't separate absorption from scattering, and measure it a few more wavelengths. And what are you going to get? You'll get water, you'll get lipid, you'll get a little bit more information content. So I think it's clear that the relative measurements, or the algorithmic-based relative measurements, have a lot of power. And they're being sold, and people are using them. So I think that's, to do the more careful, scientific, and rigorous approach, that's really to push the envelope to find out, the most amount of information that you can possibly get. Would I love to see a sensor that just does a ratiometric measurement of tissue hydration, and we have, a nice ratio of wavelengths to figure out if the adipocytes are shrinking? Absolutely. Because to do the more expensive approach and separate that and have it computationally intensive, that's impractical from a clinical point of view. Unless you can really dramatically shrink the technology, make it CMOS, make it powerful. But I think near term, there's a huge horizon, so to speak, for expanding on these platforms that are already working and add a little bit more information content. And where will the insight from that come from? From our field, the people who are pushing the envelope on being super quantitative. So absolutely, you don't need it. I mean, it all is a sort of a question of where do you want to go with it. And I think to be impactful in medicine, I don't think you need it. Yeah. Robert.
Speaking back to the beginning of your presentation, you were touching on how optical medical imaging systems are not widely known or understood from the practice from the medical side of things. So I'm interested to hear from your standpoint if you think that, given the promising nature of it, to get it into their hands, do you think we should be helping to transition it straight to the doctors, or do we need to be approaching it from the next generation side of things and introducing it into their medical residency, their training before becoming the physician?
Yeah, so that's a really good question, and I think it's impractical to really have a big impact on academic clinicians who are super busy. Just like it's pretty impractical to have an impact on, you know, the PhD scientists who are super busy. The ones who are doing all the work are you guys, the younger people, and those are going to be students and residents and fellows. So, but they eventually will transform the way the physicians are thinking. So if they're excited about it and they become champions, now there'll be, of course, you know, companies like to sort of capture thought leaders who are the super busy clinicians who are more open and adventuresome about accepting new things. So they have to sort of be approached and integrated into this process as well. But from the ground level foot soldier point of view, absolutely, you know, it needs the engagement of younger people who are trying to build careers and discover things and be excited about stuff. So we kind of have had an experiment in the sense of that going on here, because we have such a close connection to the clinic and we're embedded in the medical school. So we have biophotonics. Everybody here knows about biophotonics. People at the medical center know about optics and photonics. It's very normal at UCI. Now, probably not the super frontline clinicians, maybe they haven't heard of some of this stuff, but most of the faculty in all the different disciplines, whether it's cardiology or plastic surgery or oncology, they know about this stuff. And it's largely because of the proximity and the sort of many interactions with residents and fellows and medical students, MD, PhD students. So that does have to absolutely take place. And it also depends on who's driving it. So if it's a company that's driving it, of course, companies have to get thought leaders who are typically not the resident or fellow. So it's a combination of the two. Maybe some of our folks from companies may want to comment about that.
Excuse me.
No comment? But you're in, you said you're doing surgery a lot, or you're hanging out with surgeons, and so we're talking about your surgical experiences. You're doing surgery a lot.
Not me personally.
But I mean, you're in the surgery setting.
Yes.
Yeah. Working with surgeons. Are they all senior surgeons, or are they young surgeons, or?
That's the thing I don't know.
Yeah.
John.
Yeah. Well, and I think younger people, in a sense, are, you know, more likely to be embracing of new things anyway. So they're looking for opportunities to distinguish themselves. So if you're seeking out collaborations, I think you may have an easier time with people that are in earlier parts of their career. But I think it depends on the technology too, and how different it is, how radical it is from an established approach. Yeah.
Just as a counterpoint to what you were just saying,
Yeah.
I think you're probably correct. It's definitely easier in general to get younger people or people that are newer in a field to adopt a different technology. But it seems like it might be easier to get them into that position with a little more acceptance from people who are more established in the field, because especially in a student setting, you know, very often what your advisor, what your boss wants you to look at is what you look at.
Yeah.
They have a big impact on how your perspective grows.
Yeah. So for sure, like all of your job is to convince that your advisors, and you probably have done a good job of that because you're all here, that what you think is important is really important. And you know, I think most people will really want and encourage the kind of the passion and excitement coming from the students, and advisors expect that students will become, you know, the expert in whatever it is that you're working on, and eventually teach the advisor. Not eventually, actually, from the very beginning, about that particular area that you're going into. So it's a two-way street for sure. But I guess maybe Robert's question is very specific about medicine, which is a unique culture. It's not like what we do in research, and it's complicated. So for sure, there's a more hierarchical. Medicine is more like the army or the military, and if the commander is not happy with it, then nothing will happen. So you do have to convince the top of the pyramid that it's a good idea. No question about it. All right, thanks.